Let's look at some performance metrics of the ADC. What you will find as we look at these performance metrics that they are very similar to the performance metrics that we use for DACs. Okay, so let's take a look at them. So here we are plotting the input-output characteristic of a ADC. So on the x-axis we have the analog input, and on the y-axis you have the digital output. And just like in the previous case, we have this dashed line which joins the maximum analog input point and the minimum analog input point with a straight line. Okay, so the first performance metric would be differential nonlinearity. So the differential nonlinearity is basically how different is one LSB. So okay, let's put it this way: every step uh, in this characteristic would ideally be of the same size, right? So all these lengths are supposed to be the same, but the differential nonlinearity is the maximum deviation from that length that we want. Okay, that would ideally have been there. So that's the differential nonlinearity. It tells you what is the maximum error in that one interval, in the width of one interval. Okay, integral nonlinearity is the maximum deviation from this straight line. We looked at the same thing in the case of DAX as well. The offset is basically their digital output when the analog input is 0. Ideally there will be no offset, but in most ADCs you will have some kind of an offset. The gain error is the uh, change of this line from the ideal line, which usually is a unity, which is at 45 degrees, right? The slope of the characteristic should be at 45 degrees. And the difference of that ideal characteristic from this line would be the gain error. So how does the gain change? What is the error in the gain? Of course, you can talk about signal to noise ratio and signal to noise plus distortion ratio. They are very similar to DAX. What we are thinking about is when we are giving a sine wave input to our analog, uh, to our ADC, what is the noise that you get at an output? And what is the noise plus distortion that you get at the output? So those would give you the signal to noise ratio. The signal power over the noise power would give you the signal to noise ratio. Signal power over the noise power plus the distortion power would give you the signal to noise plus distortion ratio. Because of the noise in an ADC, uh, we have already looked that the SNR, the peak SNR, is dependent on the number of bits, right? You can actually reverse this and say, well, if there is a particular SNR, what would be the number of bits that could be effectively resolved by that ADC, right? So that is called the effective number of bits. So if the noise is very high in a particular ADC, then what would happen is even if you increase the number of bits, it really doesn't make any difference because the analog signal is then buried in the noise and you can't really differentiate between two analog values which are below the noise threshold. So the effective number of bits is as so the amount of noise or the amount of loss that you get when you quantize a signal is not only dependent on the number of bits that you use, but also the noise in the signal. If you have a higher noise, there's no point in going to a very, very high number of bits. Because even if you do that, you can't distinguish between two analog values. So that's the effective number of bits. Okay. So what that basically means is that if your signal has a noise, that you can keep increasing the number of bits till you reach the effective number of bits. And once you reach there, increasing the number of bits doesn't improve the signal to noise ratio or the signal to noise plus distortion ratio of your analog to digital conversion. Finally, dynamic range. Dynamic range is basically, we were talking about noise threshold and the amount of noise that there is in the signal. So if there is an amount of noise, any variation in the analog signal within that noise level is not going to register in the ADC, right? So dynamic range is this noise threshold till the maximum signal. So this is a very small signal, smaller than the noise there is. The ADC cannot really convert this signal into a digital value. It cannot do it. So your signal has to be bigger than this noise threshold to actually see the difference in the signal for the ADC to work. So that's the minimum signal you can convert. And the maximum signal that you can convert is the full range of your ADC. So that gives you kind of the range of inputs that the ADC works for. And that is given by your dynamic range.